Okay, so now we've got a couple more demos. Actually, it's a total of 4. We're going to start off with the hydrogen peroxide demo. The hydrogen peroxide demo is an example of reaction types. Remember, we talked about these reaction types. Which one is it? So think about that. Hydrogen peroxide is a funny chemical. H2O2, kind of a funny looking chemical. Kind of looks like it should be this one, right? It should be regular old water. Well, what does it have to lose to become like water? It has to lose one of those oxygen. So if it loses an oxygen, well, then the oxygen flies away. Well, oxygen has to be like this, actually, O2, right? Oxygen has to be like this. And what we are left behind with is water. So how are we going to get this started? Well, actually, it's already started in here. This reaction is already going. So I'm going to lower in the thermometer, and we're going to see what the temperature of this reaction is. Right in there. Down deep, but not touching the bottom. It's got to be in there, but not touching the bottom. And the temperature of this reaction is 23 degrees Celsius. Okay? So let's just watch this reaction. Let's just watch it. But that's kind of boring. It's a very slow reaction. So what we're going to do to speed it up, oh, I've got something here. I've got something we can use. I've got a little catalyst. Catalyst is a chemical which speeds up reactions. Well, this catalyst is called manganese dioxide, MnO2. Don't get that confused. That's not magnesium. That's manganese, and it looks like a powder. Let me take a scoop out. It looks like a little gray powder, okay? So what I'm going to do is I'm going to add some, and we're going to see this reaction accelerate, because this is a catalyst. So watch, I'm putting a little more in, a little bit in. Now notice, we see a reaction. It's happening way faster now because of the catalyst. Also, you see some sort of fog developing there. So that looks like that should be oxygen, right? Should be oxygen, right? But actually, oxygen is completely invisible. Think about it. You're breathing oxygen right now. You can't see the oxygen in front of you. So oxygen is invisible. What you're actually seeing there, what you almost always see when you think you're seeing a lot of gases, it's actually water. It's actually water turning back into liquid in the air. So I'm going to add more now. That's not enough. I'm going to put more of the scoop in, and we're going to see this reaction speed up. So now notice, this is the reaction. We're producing oxygen and water. So maybe some of that is water vapor, but actually you can't see water vapor either. You're seeing it when it turns back into liquid. So what's the temperature on here? Well, now it's getting up to 30. It's rising.
It's like going up, bouncing.
Is that a pretty good reaction?
It's like bouncing.
It's like bouncing. And it's splattering a bit. This always happens with this reaction. So the great thing about that reaction is that provides us with one of the things we need for our next reaction, which is actually the oxygen. That's one of the things we need. So I'm going to let that reaction keep going. That will, if anything, that's going to accelerate our next demo. Okay? So notice I'm not in harm's way being right here, because what's being given off is actually oxygen and water. That's what that is. So I'm not being harmed here, but there's extra oxygen in this area. Maybe we can take advantage of that in our next demo. The next demo is the Magnesium Demo. Okay, magnesium is an alkaline earth metal. Magnesium is an alkaline earth metal, and it usually comes in ribbons like this. Okay, we find that the good stuff, for some reason, comes from India now. This is a ribbon of magnesium. Remember, metals are malleable. Metals are ductile. So you can make them into wires, and you can make them into sheets. Well, guess what? A ribbon is a little bit of both. It's almost as thin as a wire, and it's as flat as a sheet. So here's a little piece of magnesium metal. The problem is it's in the presence of oxygen, which is what it needs to react, but it's not reacting. To start this reaction off, we are going to have another reaction that's easier to start. So let me find another reaction that's really easy to start. I'll move this out of the way. Oh, you know what's easy to start? A safety match. That's why matches were created, because they're really easy to start. Okay? So lighting a match is actually a chemical reaction. So to see this one, I'm going to turn the light off right there. So I'm going to light the match, and then I'm going to use the match to light my stovetop. Okay? That's going to ignite the methane, mostly methane, that comes out of the stovetop. That reaction will get going, and then I'm going to use that reaction to start my magnesium ribbon, which will take advantage of this extra oxygen that has been introduced from my previous demo, if it's still in the air, if it's still in this area. Okay? So this is actually 3 reactions. One of them is lighting the safety match. The second one is burning the stovetop. Normally we would use Bunsen burners, but this is a same gas, the natural gas, mostly methane. By the way, methane doesn't smell. They put a little additive that really stinks so we can detect gas leaks, by the way. That's not the methane that you're smelling. So first of all, let me turn this on a little, and then I'm going to light the match. That's one reaction. Second reaction. Okay, put the match out. Now I'm going to use that to light the magnesium ribbon. Now this is a very bright reaction, so just make sure to avert, those of you that are in the room, my kids, just don't stare at it for too long. Try to avert your vision. Okay, you want to see it, but you want to also not blind yourself. Okay, so this one is a little harder to get started on a stovetop than it is with a Bunsen burner. There we go. So now I got 2. It's like a binary star. Is that as bright as the sun? Look at all these shadows. See the shadows forming? Look at all these shadows forming. That's what they use in flares. This is a really good one. This is a really, really good one. Okay, I'm going to have to turn on the expeller fan. Okay, this is a really, really good one. It's burning brightly, maybe because of that extra oxygen. Maybe because of that extra oxygen that is here. This one's going for a long time, a really long time, right? Okay, that is a great reaction, a great example of an alkaline earth metal demo. Let me shut off the stovetop. And notice how bright that was. That was, if depending on your distance, I'm a little dazzled right now myself. That was as bright as the sun, and I did 2 ribbons, so it was kind of like a binary star. Well, there's the magnesium oxide. Lots of chemicals oxidize, and then they form compounds with oxygen. Lots of chemicals react with oxygen. Magnesium is no exception. So remember that you need to determine what reaction type that was. Of those reaction types, which type of reaction was lighting the match, which type of reaction was the actual stove burning, the gas burning, the methane, and the magnesium, the alkaline earth metal. Okay. The other one, of course, was the hydrogen peroxide that we did first, and that reaction is now pretty much over. So look over here. What's left? Oh, no, it's still going. And our temperature, oh yeah, look, 85 degrees. It reached 85 degrees Celsius, so it took a while to get there. I think that might be the maximum temperature. Shut this off. I think that might be the maximum temperature for the hydrogen peroxide, about 85 degrees. Yeah, because now it's going down to 84. So I think, and it's actually still bubbling just a little bit in there, getting close. See, it's really just bubbling a little bit in there. And what's left in there is actually the catalyst is still in there, because catalysts are not directly involved in the reaction. Catalysts are still in there, and water. So if we used up all the hydrogen peroxide, then what we really have left in here when this is done is water and the catalyst floating around. It should settle on the bottom. So in a few minutes I'll get another shot of it after it has settled out on the bottom. Okay, thank you guys. Thanks for doing the demo with me.
Yeah.
Now you can see a few minutes later that it is just water. You can see right through it, and the catalyst has settled on the bottom. The catalyst was there, but was sort of a bystander. That's why it is left out of this reaction. So you don't consider the catalyst when you're figuring out the reaction type or balancing.